Hello everyone, this is Dr. Hopkins with your next video in the series. Here we're going to still continue with acids and bases, but introduce a measure of acidity and basicity, so pH and pOH. Now pH is actually kind of a relic from an era when you had slide rules and we didn't have calculators. Everybody didn't have a calculator that could do really easy small numbers. But because the concentrations of acids in water are typically very small, we're talking 10 to the minus 2 to, 10 to the minus 12, 10 to the minus 14, whatever it might be. So those are very small numbers, very hard to visualize, very hard to compare. And so you could make a logarithmic scale and make it much easier. So you take 14, 10 to the minus 14 and make it 14. 14 versus 7 is much easier to compare than 6 zeros in front of a 1 or 13 zeros in front of a 1 in the day when we didn't have ubiquitous calculators. All right, so the two scales are pH is the negative log of the H3O plus concentration, that's in molarity, and the pOH is the negative log of the molar concentration of OH minus. Okay, so it's another way of representing these concentrations. So if, for example, we had an H3O plus concentration of, say, like just pure water, of 1.0 times 10 to the minus 7 molar, we would just plug that in to our logarithm and take the log of the negative log of that, and that would be 7. If we did the same thing with OH minus, let's just take an example. We're not going to use 10 to the minus 7. Let's do 10 to the minus 5. So 1 times 10 to the minus 5 molar OH. These are still very small concentrations, right? They're not very large. And so in that case, you would plug that number in, take the negative log of it, and you would get a pOH of 5. Now, it turns out that pH and pOH are related through the autoionization of water. This is one of the reactions that we talked about in the last video, discussing Bronsted-Lowry. I don't really want to go into the math of this at this point, but we will eventually. But basically, the sum of pH and pOH in any solution is equal to 14 because of the presence of water. So if we take our pOH of 5, we can turn it into pH by subtracting 5 from 14, and we get a pH of 9. Now notice we had a larger concentration of OH than we did in H3O plus, so a pH of 9 versus a pH of 7. So what does that mean in terms of the acidity or basicity of a solution? So if you have a solution that has a pH of less than 7, so that means they're larger than 10 to the minus 7 molar H3O plus, it's considered acidic. Okay, in that case we have more H3O plus than OH minus, because remember our limiting factor is that 14. If we have a pH greater than 7, it's a basic solution, and that means that basically we have more OH minus present than we have H3O plus. Okay, and if they're equal, the solution is a pH of 7, and it's neutral. Okay, so let's do some calculations with these. So let's take strong acids and strong bases, what we left off with in the last video. And remember, what makes them strong acids and strong bases is they completely dissociate in water. So here we have an example of hydrochloric acid. If we put it in water, it dissociates into H+, or that's the same thing as H3O+. Remember, we're going to use those terms interchangeably. And the chloride ion. So in essence, based on this, it's 1-to-1. For every HCl, we get an H+. So our pH is going to be the concentration of the strong acid that we put into solution to begin with. So if we started with, say, a 0.01 molar HCl solution, the pH would be the negative log of 0.01, which is 2.00. Same thing for a strong base. Remember, it also completely dissociates. We write the arrow. We get 1 OH minus for every sodium hydroxide we put in solution. So our pOH is the concentration of the strong base. Let's do the same concentration. Let's make it 0.01 molar sodium hydroxide. That gives us a pOH of 2, just like we had pH of 2 above. And the pH is just 14 minus 2, which is 12. Okay, so we have a very basic solution for the strong base. And for the strong acid, we have a very acidic solution. So what about if we have a weak acid? Okay, so if an acid's not among those 7 strong acids, remember that was a list that and the strong bases, that was a list that I wanted you to learn. You need to memorize that, because if it's not one of those strong acids, that means it's weak. If it's weak, that means it's a weak electrolyte. In other words, it does not completely dissociate in solution. In this case, we're talking about aqueous solutions, and actually in all of 106, we're going to talk about aqueous solutions. So it means that this does not completely dissociate. We're going to have some of the molecular components still left. So we write our dissociation of a weak acid in water the same way we started out writing our Bronsted-Lowry acids and bases. So we put our general weak acid, just going to be HA. We add it with water. We get H3O plus, which is the conjugate acid of water, and then we get A minus, which is the conjugate base of the weak acid. Now we're going to have to keep this as an equilibrium. So if we wanted to know the H3O plus concentration and the pH, we would need an equilibrium constant. Well, it's a good thing we actually know how to get equilibrium constants. So one thing, we could determine the delta G of this reaction using the delta G deformations of all of the components of this reaction if we wanted, and then we could use minus RT natural log K and determine that K. And that's fine, and it's good that we know how to do that, but it turns out someone else has done that, and they've made tables of acid dissociation equilibrium constants. So we're going to look up, and these are going to be specifically called Ka, so that A stands for the acid dissociation. So we would look up a K in a table. We'd either Google it or use your book, and so forth. So you'll find this K for a weak acid. So when we want to determine the pH of a weak acid, since we are at equilibrium, we already know how to solve for all the equilibrium concentrations, and one of the concentrations is the H3O plus, or the pH, so we're going to use ice tables. So let's do a problem where we're going to determine the pH of a 0.050 molar hydrofluoric acid solution that has a Ka of 6.4 times 10 to the minus 4, which I looked up in a table at the back of your book. All right, so here we have our HF. We have the equilibrium set up. I've got my ice table set up already. We just need to input the numbers. So remember, we're solving this for a 0.050 molar HF solution. Initially, the water concentration, remember, water doesn't factor into our equilibrium. It's a pure liquid, so we're going to get rid of that one. H3O plus, we start with 0. F minus, we also start with 0 initially. And then we set up our algebra problem just like we did in our ice tables before. So minus x, these are all 1 to 1. So those are plus x and plus x. So that's x and x for those two. And then 0.050 minus x is our final concentration, or equilibrium concentration, of HF. So now let's write out our equilibrium expression. So we have H3O plus concentration times F minus concentration, those are our products, over our reactants, which is HF concentration. And that was, what, 6.4 times 10 to the minus 4. So we'll substitute in our two x's and our 0.05 minus x, so that's going to be x squared over 0.050 minus x equals 6.4 times 10 to the minus 4. Now at this point, I don't think we can assume that the x is small compared to 0.05, so we need to multiply this out and solve the quadratic. Okay, so I'm going to go ahead and simplify this for you. So that's x squared plus 6.4 times 10 to the minus 4 times x minus 3.2, which is the 0.05 times 6.4 times 10 to the minus 5, okay, equals 0. All right, so that's our equation, and then if we plug those into the quadratic to solve, we get x equals 0.0053 as our concentration. That is our H3O plus concentration. which if we take the pH equals negative log of 0.0053, or 5.3 times 10 to the minus 3, it's going to equal 2.28. So that's our pH of our 0.05 molar HF solution. And lastly, we have our key takeaways from today's video, that we've introduced a new measure of concentration of acids, pH and pOH. We've determined the easiest way to determine the pH of a strong acid is just the concentration of the strong acid, negative log of that. And then if we wanted to know the pH of a weak acid, we have to do an equilibrium calculation using ice tables. We have to determine a Ka from a table, and we have to use more of that useful algebra. So until next time.